Hello everyone. Okay, so in this video, we're going to be covering tree diagrams, and I'm going to be showing you how to draw the tree diagram to predict the coupling for HB in this case. There are other cases over here, but we're going to just be focusing on this problem. So we're going to it says to predict the coupling, right? But really, another way to say that is to show the splitting pattern or yeah. And we're going to be doing that by drawing the tree diagram for this proton here. So the first thing we have to look at or consider is, well, let's look at first the coupling constant. So the coupling constant in this case for both proton relationships is J equals 9 hertz. The reason I say proton relationships, that's not an actual term, I just said that, but if you look here, you see that HB has how many neighbors? Well, let me get a different color. They have 1, 2, 3 neighbors. I highlighted these two in the same color because they are identical. They're homotopic. Homotopic. Oh my god, sorry. Homotopic protons. Homotopic protons as in they are in the same chemical environment. So on an NMR, on an HNMR, a hydrogen or a proton nuclear magnetic resonance spectroscopy, they would give the same signal because they're in identical chemical environments. That is for these two, that's important. However, when we're counting the neighbors of HB in order to draw the tree diagram, we still say that HB has 1, 2, 3 neighbors. Okay? Alright. So, knowing that HB has 3 neighbors, where do we go from here? So, this is where it's important to mention. I highlighted before, but I didn't actually say that we have the same coupling constant between these neighbors and this neighbor and HB. J equals 9 hertz and J equals 9 hertz. And when you have, I'm going to write this, when you have equivalent coupling constant, which we do, n plus 1 holds true. So n plus 1 is the rule of vicinal coupling. Vicinal as in neighbor. So we have, as long as it's our neighbor, which means that the carbon that HB is attached to, just bear with me, its adjacent carbon, or the carbons next to it, the protons that it contains, would be considered the neighbors of this proton. And for that, we would use the n plus 1 rule. So if it has 3 neighbors, which it does, that's 3. 3 is n, plus 1. So our splitting pattern would be what we call a quartet. Okay? So that's why I kind of tried to emphasize the J equals 9 hertz and J equals 9 hertz. We have the same coupling constants or equivalent coupling constants. So n plus 1 would be a rule we apply here. Okay? So now knowing that, now I'm basically going to start my tree diagram. So I start by writing out HB at the top. And now I'm going to talk a little bit about the technique that I use to do this. So knowing that, sorry. Knowing that we have a quartet, right? Knowing that our splitting pattern is quartet, my technique, I tell myself, is we're going to split the tree diagram 3 times, right? Just the same way that HB has three neighbors, that means we have a quartet signal because of 3 plus 1, n plus 1, right? However, in the tree diagram, in order to show a quartet splitting pattern, we're going to split the tree 3 times. So 1, 2, 3. And you'll see what I mean. I'll do it really quickly just for the sake of demonstration. 3. But now let's really do it. So, first split. And it's going to happen 3 times because we have a quartet, right? And if we had a, let's say, okay, really fast. If we had a triplet, how many times would we split it? 2 times, right? In this case, we have a quartet, so let's split it 3 times. So first split, we go like this. That's going to be 1 to 1, right? Now, that's just the 1 and the 1 I drew there, that's just the integration, right? But what is important to write right here in the center is the coupling constant, right? So it's going to be 9 hertz. This, by the way, before I continue, this is usually a lot easier to do on graph paper because you could actually pick 9 boxes, like 9 little boxes, and like say, okay, so it's 9 hertz. And then when you split it again, you could pick another 9 little boxes and you could say 9 hertz. But you could still do it without graph paper, which is what I'm going to do right now. I just wanted to mention if you could use graph paper, it would be preferable. So we split it once, and we have to split it 3 times, right? Because we have a quartet. So let's split it again. So over here, I'm going to split it again, split it here. This is going to be 9 hertz, right? This is my second time splitting it. Well, I'm about to finish now. Okay, so something just happened here. I'm going to split it here. When I came and split this line here, this part of it, by the way, this is all still 1 to 1, but this is my second, this entire thing is my second time splitting it. I split it here and I split it here, and that's my second split. So we have one more to go. But something happened here that I want to mention. When I came here and I split right here, and then I came here and I split right here, these lines overlapped. Okay, so I'm going to highlight it so you could note that there's 2 lines here on top of each other. That way it's not confusing later. Let me make a key. So 2 lines. Okay, let's keep going. So this is going to be our last time splitting the entire row because we have a quartet, right? So I know I've probably mentioned that like 5 times already. So let's split it here. Actually, you see, I'm having a hard time because I don't have graph paper, but that's okay. We can do it. Split it again on the other side. Okay, now, in the middle, remember that there's 2 lines. We marked it, right? So, you're going to split one line, one of the 2 lines. Let me choose a different color. Let's say this is the first line. We're going to split first one of the 2 lines and the other side, right? And then we're going to split the other of the 2 lines. Let me pick a different color. The other one. So this side and this side. Okay, let me switch back. And then this line again, you're going to split both sides. Like that. Now, right here at these positions, this is where we're going to place our peak intensities. And peak intensities is essentially what? Peak intensities is in tree diagrams. Oh, let me also say this is all 9 hertz. The coupling constant remains 9 hertz for all of these. It's not to scale. Obviously, I don't have graph paper, so I wasn't able to make it all exactly 9, but just for for our purpose, imagine these were all the same size. So, back to what I was saying about the peak intensity. This is essentially here is where we're going to write our peak intensities. And what is our peak intensities? It's how many lines there are on basically in this whole row. So here we have one, there's one line. Here we have three lines, right? Because when we had two lines up here, we then had to split both those two lines and the same thing with the other line, and it ended up giving us 1, 2, 3 lines. So this is going to be 3. Same thing with this one. This is going to be 3, and this one's going to be 1. So our splitting pattern, our quartet, right, splitting pattern, is going to be 1, 3, 3, 1. And if you look, there's 1, 2, 3, 4 peaks for quartet. And that would be how you draw the tree diagram to predict the coupling or to show the splitting pattern for HB.